Jnanam Paramam Dheyam. Knowledge is supreme.
Okay. All right. So, what is m by m square? That is what we have to understand. So, m by m square. So, this is so this m is image of p after localization, right? And this is m square. But remember, image of p after localization not in a polynomial ring, but in a mod A. So, therefore, this is same as, I will write once only because it is not 2. So, this is p k x, x means many variables, then localize at p, and modulo you have to go that image of A, right. So, this is A k x p, this is m, and now I have to go mod m square. That means square of this ideal, but when you take square of that, the p square may not contain A. So, you will have to add that, right. So, this means this, the square of this is square of this. So, p square k x localized at p plus A. And mod A, of course. Right. This is what we have to go mod. So, when you go mod, then this will get, so this is same as, allow me to write a short form for this. So, I will write a short form is p suffix p, this is p k x localized at p. If you use this short form, then this is nothing but p mod AP, and then you are going mod p square p plus A, and mod A, this is also suffix p, this is it. I just copied it in this notation, but this is same as p mod, so this will go away. So, this is p square p plus AP, this is it, right. This will go away, this and this will go. So, this quotient. Now, we want to compute the dimension of this. So, the dimension of this, so you see here, it's p square p is here, this is contained in p square p plus AP, and this is contained in PAP, PP, and this dimension you want to compute, but this is better, right. So, therefore, this dimension, so I will write, so dimension of, as a L vector space, m by m square is equal to this is what I want, this is what we want. So, the dimension will be this minus this, right. So, I am just writing that is dimension of p mod p square p minus dimension of A localized at P plus P square P mod P square P. I have not done anything great, it is only complicated. See, this we are interested in this dimension. So, I have written this dimension equal to this dimension minus this dimension. Alright, but what is this? So, isn't this bigger equal to height of P? This part. You see, because where is this? This is now in a polynomial ring x1 to xn, localize it, and this ring I know the dimension is height P, and this is the embedding dimension. So, it's actually equal to minus, and this one is height of Q, bigger equal to, because you see, because this A is here contained in P, contained in Q, contained in P. So, it is localized, so nothing is happening after that, and before that it is only Q. So, Q is one of the minimal prime. So, the dimension will be, this is minus sign. So, it will be less equal to height. So, it is this is clear. And when will equality will happen here? Precisely equality will happen here. So, equality here if and only if R is regular. That is because you see we have noted here the dimension of m by m square is bigger equal to height P minus height Q. So, if equality happens here, that means dimension of m by m square is equal to dimension of R, and therefore R is regular. Equality if and only if R is regular. So, therefore, that okay. So, we got when is R regular in terms of this height P and height Q, when the equality holds here. Okay, now therefore, we only have to tie up with the rank of the matrix. Okay, that is, and I will remind you what did we prove in lemma 1 and what did we prove in lemma 2. Okay, so in the lemma 1, we have proved the following. This was precisely content of the lemma, not exactly, but it will be this will be the outcome of that. So, this ring, polynomial ring, localized at P, this is regular. If and only if height of P, that is the dimension, and the embedding dimension, that means localized, that means this should be equal to dimension of over L of P mod P square P. That is when this is regular. This is only a definition. This is what we have by lemma 1. And lemma 2 was rank of this matrix, the Jacobian dFi dxj mod P. This rank was less equal to the dimension of, because you see this is AQ, A localized at P plus P square P modulo P square P, which is less equal to height P, height Q. That is what we have proved in lemma 2, and also we have proved equality here if and only if R is regular. So, equality if and only if R is regular. So, that precisely what we want. You see here, because this one is bounded by this one bounded. So, when equality holds here, that means equality hold here, and this equality holds, that means equality here hold here will mean that R is regular. So, just tie up both these things and then you get the answer. So, that proves your A and then everything. Now, let me just discuss couple of examples. So, first of all, I want to show example where the separability issues. Okay, so example. Okay, so let us take K to be the prime field Z mod P and the rational function field in one variable. Rational function field over Z mod P, and let me take only one polynomial f. This is our ideal A. So, f is the polynomial x power p minus t, where p is this characteristic. Alright, and what I have to give you also p, and we are testing at p. So, p I want, and also I want q. So, A is ideal generated by f, that is also ideal generated, that is also p, and that is also q. Let us take this equation. Note that p is a prime ideal because f is irreducible. F is irreducible because f doesn't have, t doesn't have p through. So, this is irreducible in Z mod P T X. This field is not perfect, it is ZPT, because you see if you take the pth power map, the T doesn't have pth roots. Okay. So, that is this. So, now what is our ring A? A is K x mod f. F is irreducible, this is a PID, therefore, this is actually a field. Ring is a field, but the fields are regular local, and hence regular local. Fields are local because 0 is the only maximal ideal, or 0 is the only ideal, and this is regular local. So, A is regular local. Now, let us see the Jacobian matrix and the rank. So, but Jacobian matrix is now df, there is only one equation, so only one entry. So, this is 1 cross 1 matrix, and this I have to read mod P, right. But what is this? What is first of all df by dx? I have to differentiate with respect to x. That means this is p times x power p minus 1, and t is treated as constant, but this is 0 because p is a characteristic. So, actually this is a 0 matrix. 0 matrix has rank. So, the rank is the rank of this matrix rank is 0, and what is the height? Height of Q, it is a principal ideal in a polynomial ring. So, height is 1. So, this is strictly less than 1, which is height of Q. So, therefore, in the C part, that the converse of B does not hold, because this is the example. Okay, now let us take some more examples. so that one will realize that how important it is for the calculation. Okay, let us take next example. Okay, let us take this cusp. You remember the cusp, that is looking at the equation f, which is x1 cube minus x2 square. Remember this example? Right? This is called a cusp. And if you increase the power here, that will go more and more touching. So, if for example, if you go x power 5 minus x1 x1 power 5 minus x2 square, the diagram should become more closer to the axis. If you go higher power, it is even more. And so, if you go larger power, the picture will look like this. It will get closer and closer. Okay, so we are looking at this. The same thing will happen for the other examples also. I want to compute exactly how many points are singular and which are they. So, for that we will have to compute the Jacobian matrix and the rank. Okay, so what we are doing? So, first we have to compute the Jacobian matrix. Okay, the Jacobian matrix will be the partial derivative. So, only one equation. So, it will be df by dx1 comma df by dx2, these two, right? And then we have to read the mod somebody, right? Mod the prime ideals which you want to test, whichever is singular or not. So, and we are working in this ring, this affine ring, k x1 x2 mod f. So, this is, in any case, this is one dimensional. So, therefore, and 0 is the prime ideal there, and the maximal ideals. There is no in between. Okay, so these partial derivatives are what? These are, this is 3x1 square comma minus 2x2. So, we are looking for now solutions. So, also we want to look for, so they are only, let's also assume, if you want to assume algebraically close, or it is not necessary. So, let us take a point, we are testing whether the point a1 a2, whether this is singular or not. So, when I plug it here, it should become, rank should become 0, right. So, that means, so this x2 is already 0, this coordinate is at this point, the rank should be 0 or 1, that is only the question, right. So, at this point, this A2, when the rank is 0, then this coordinate is 0, means x2 is A2, and this one, if it is 0, then x1 is also 0, right, and that is going through this also, right. So, you have to check all those things. So, the only possibility is 0 0, because if you take any other than 0 0 point, then either x1 coordinate is non-zero or x2 coordinate is non-zero, then one of them is non-zero, and therefore, rank will become 1, and then that criterion will tell you then it is regular ring. Therefore, the only singular point is 0 0. Okay, one more. So, for example, if you take now the other example, that is x2 square minus x1 square plus x1, this one. Remember, this picture was like this, something like this. So, in the picture you can see there is no singular point. So, singular locus should be empty here, right. So, that also you can see it by differentiate. So, differentiate it, then what is the matrix you will land up into? First the differentiation with respect to x1, that is this. So, that is minus 3x1 square minus 1, that is the first entry. The next one is 2x2 square, 2x2. Okay, so when is it singular? If I take the point a1, a2, and if it is singular, then that means x2 is a2. I am looking at the singular points. Singular means rank is strictly smaller. So, this is x2 will be a2, and then this also I want non-zero. This also you want 0, but that will get solved for x1, right. So, that we will get at the singular point x1 will be then equal to, we shift it to the side 1 by 3 and the square root of 1 by 3, because this should be 0. See, if it is non-zero, it will be non-singular, because the rank will be 1 and it will be therefore non-singular by the criterion. So, in order that the point, this point to be singular, both these should vanish at this point. At this point they vanish, means x2 is a2, and this is at when I plug it x1 equal to a1, it should become 0. So, that means x1 is square root of 1 by 3, but then it does not pass through that curve. Oh, so I need 3 a1 square minus a1 is 0, right. This means a1 equal to a1 square equal to 1 by 3, right, is not it? No, this go to the minus. So, it depends on the field. Even if you would have worked with complex numbers, it is something, but then this point will not pass through this curve, because see, when you are putting a1, so here you put a2 and here you put something which is this, so this is not 0. So, it is, so the only singular point is nobody singular, therefore singular locus is empty. Just check that this solution which we got by taking the Jacobian matrix to be 0 matrix, that will not pass through the curve. So, therefore it has no singular. Okay, so this I want to do more conceptual example. For example, elliptic curve. So, elliptic curve means what? It is a curve like this, x2 square minus fx, where fx is cubic, x1 cube, fx1 is x1 cube plus some ax1 plus b, cubic like this. And now, and let us assume also the characteristic of the field is not 2. This is needed because otherwise you do not have good formulas for the quadratic equations rule. If you have a characteristic 2 field, how do you write the zeros of the quadratic equation? Okay. So, what is the Jacobian matrix here? Jacobian matrix is 2x 2, no, Jacobian matrix is differentiating with respect to first one is x1, right. So, that is f prime at x1 minus, and the second coordinate is 2x2. This is the Jacobian matrix, and we are now suppose a1 a2 is singular point. A1 A2 is singular, if A1 A2 is singular, that means the Jacobian matrix should become 0, because see, we are in which ring? We are in the ring, polynomial ring in two variables x1 x2 modulo this equation x2 square minus f, this is equation f of x1, right. So, the dimension is 1 of this ring. So, the only possibility is the Jacobian matrix is 0 0 matrix. No? So, then, so when do singular points exist? That means this when I plug this, it should become 0. That means the condition is x2 equal to a2 and this should be a2 should be 0, because this coordinate should be 0, characteristic is not 2, therefore a2 should be 0, and f prime at a1 should also be 0. Again, we are using characteristic is not 2 because plus minus, no. So, this is 0, but this condition is what? This means this is a cubic equation and the derivative is vanishing at here. So, this is equivalent to saying, so this means, so that is this a1 and that a1 a2 also should pass through this curve. So, that means a2 square minus f of a1 should be 0, this is also there, and this is 0. So, a2 is 0, therefore, f of a1 is also 0. So, f of a1 is 0 and f prime at a1 is 0 also, that means the discriminant of f is 0, because common roots of f and f prime are precisely the, okay. So, discriminant f is 0, but what is discriminant? Discriminant is 4a cube plus 27b square, that is the discriminant of the cubic equation. So, such a curve is called a cubic curve, such a curve is called elliptic curve. So, that means, so you would probably learn somewhere that cubic elliptic curves are precisely x1 x2 square equal to cubic polynomial with a distinct zeros, but that how that is, because we want a non-singularity, it is a non-singular. So, what we checked is this curve has no singular point. So, that means the curve is non-singular. So, that means this curve, that means x2 square minus f x1 equal to 0 is non-singular curve. And you see the degree of this polynomial, as a polynomial in x1 and x2, degree is 3. So, degree of this is 3. So, such curves are called elliptic curves. There is an abstract definition of elliptic curves, and then one says that if you put them in the coordinates, it will become this one. Another example, so these are geometry examples, but also it is interesting to compute. So, if you look at the ring A, now this is not an affine algebra, z root minus 3. Now, what is question is, what is the singular locus, sing A. That means, what are all those primordials P? So, this is all those P such that AP is not regular. Right, this is one dimensional ring. So, again it is only so I will not complete the calculation here, it is not so difficult, but what will keep handy is note that this ring A is not A, the Z 1 plus minus square root 3 divided by 2. So, this is contained here. Why is this thing important? This is precisely the normalization. This is A bar. This is the integral closure of A in its quotient field. What is the quotient field? Quotient field is precisely q root minus 3. This is the integral closure. That is not too difficult to see. This integral closure, and we have seen in a one dimensional case, normal and regular is same. So, this is regular actually. This is regular. It is not local, but so what might help you now to decide what is the singular locus of A is note that this A bar is Euclidean domain. If you use that, then and you try to check your prime ideals which are singular, the answer you will get is the following. Sing A is precisely only one point, namely the ideal generated by 2 and 1 plus root minus 3. We check that this is prime ideal and this is the only prime ideal. When you localize this thing there, it becomes non-regular. Other are regular. This is not too difficult to check, but it will be very handy for you if you use this. Okay, so I will leave it for you to check this. This is interesting calculation. Okay.